In the heart of Alexandria, where the warm Mediterranean winds carried scents of papyrus, salt, and distant lands, a man peered at the heavens and the earth simultaneously. Claudius Ptolemy, scholar, mathematician, and astronomer, lived in a city that had long been a hub of learning, a place where Greek, Egyptian, and Roman knowledge converged. The city was a labyrinth of streets filled with traders from all corners of the known world. But within the quiet chambers of its libraries, Ptolemy sought patterns invisible to most men. His task was nothing less than monumental: to chart the world as it could be known, and to measure the heavens with a precision that would endure for centuries. Born around 100 AD in Alexandria, Ptolemy's life coincided with the Roman Empire's apex. Alexandria, a city founded by Alexander the Great, was still a beacon of Hellenistic scholarship, home to a wealth of scrolls and manuscripts preserved from centuries past. Though the Library of Alexandria had suffered calamities, fragments of knowledge survived, providing Ptolemy with the intellectual tools he would need. While little is known of his personal life, the scope and depth of his work suggest a man of discipline and tireless curiosity. He navigated the world not by sailing its seas, but through numbers, geometry, and observation. Ptolemy's intellectual journey spanned multiple disciplines. Astronomy, geography, optics, and harmonics all bore his mark. His works combined inherited knowledge with his own meticulous reasoning, producing systems that would guide scholars for over a millennium. Among his most influential contributions were the Almagest and the Geographia. Each represented a monumental attempt to impose order on the cosmos and the Earth through mathematics. The Almagest, originally titled Mathematic Syntaxes, was Ptolemy's masterwork on the motion of the stars and planets. In it, he codified a geocentric model of the universe, one in which the Earth rested immobile at the center and all celestial bodies revolved around it. This model, although ultimately incorrect, was mathematically sophisticated. To account for the irregular movements of planets, particularly retrograde motion, where planets appear to reverse their course temporarily, Ptolemy introduced the concept of epicycles. Each planet traveled in a small circle. Epicycle, whose center moved along a larger circular path, deferent around the Earth. This system allowed predictions of planetary positions that were remarkably accurate for the era. Ptolemy meticulously catalogued over 1,000 fixed stars, documenting their positions relative to each other. Using instruments such as the astrolabe and armillary sphere, he measured angles, calculated the inclination of the ecliptic, and estimated the solar year with impressive precision. The Almagest combined observation and mathematical reasoning, establishing a framework that would dominate astronomy for centuries in both the Islamic world and Europe. Parallel to his study of the heavens, Ptolemy sought to describe the Earth with equal rigor. The Geographia was a comprehensive compilation of geographical knowledge, including coordinates for thousands of locations. Building upon the work of predecessors such as Marinus of Tyre and Eratosthenes, he introduced the concepts of latitude and longitude. Each place could be precisely located on a mathematical grid, a revolutionary approach that transformed map-making. Ptolemy's world extended from the western limits of the known Atlantic to the eastern reaches of China, and from the northern lands of Britain to Central Africa. Some of his representations were inevitably imperfect, reflecting limited first-hand knowledge. For example, he incorrectly enclosed the Indian Ocean, believing it was surrounded by land. Yet the underlying system, an ordered grid of coordinates, endured. Ptolemy's maps were not mere illustrations. They were practical instructions for reproducing the world mathematically. He devised methods for projecting the curved surface of the Earth onto a flat plane, introducing early forms of map projection that influenced cartography for centuries. The structure of his maps allowed future explorers to place newly discovered lands within an ordered system, even when the scale or exact positions were unknown. His curiosity extended beyond geography and astronomy. In optics, Ptolemy explored the properties of light and vision. He conducted experiments on reflection and refraction, studying how light bends through various media. His observations on visual perception were among the earliest scientific investigations into the human eye and the nature of sight. Similarly, in harmonics, he examined musical theory through mathematical ratios, continuing the Pythagorean tradition that saw number as the foundation of both cosmic and musical harmony. Ptolemy believed that the universe followed a rational structure, and that through careful measurement and reasoning, humans could comprehend its order. Ptolemy's intellectual environment in Alexandria was unique. The city was a crossroads of culture, with Greek, Roman, and Egyptian influences intertwined. Scholars, philosophers, and merchants all contributed to the exchange of knowledge. The libraries and schools provided access to centuries of accumulated wisdom, allowing Ptolemy to study the works of Aristotle, Hipparchus, and earlier geographers. Though Alexandria's political and cultural influence was beginning to wane, its scholarly tradition remained vibrant during his lifetime. The impact of Ptolemy's work was magnified by the preservation and translation of his texts. During the Abbasid Caliphate, scholars in Baghdad translated the Almagest into Arabic, calling it Al-Majisti, the greatest. These translations preserved his astronomical tables, star catalogues, and geometrical methods. Islamic scholars such as al-Battani and al-Sufi built upon his work, correcting errors and expanding knowledge while retaining Ptolemy's rigorous approach. The Geographia similarly survived, later translated into Latin during the 12th and 15th centuries, providing a foundation for Renaissance cartography. Ptolemy's system of coordinates and projections informed the work of Renaissance mapmakers, including Martin Waldseemüller and Gerardus Mercator. Even as exploration revealed the vastness of the Earth beyond his maps, the principles he introduced, systematic measurement, mathematical projection, and the conceptual grid, remained indispensable. His errors, such as underestimating the size of the Earth, influenced historical events, including voyages of discovery led by Columbus and others. Despite living almost 2 millennia ago, Ptolemy's methods resonate in modern science. His insistence on combining observation with mathematical reasoning set a precedent for scientific inquiry. While his conclusions were not always correct, the framework he provided enabled successive generations to improve upon his work. In astronomy, navigation, and cartography, his influence endures. Globes, maps, and celestial charts continue to reflect principles first articulated in Alexandria, in the mind of a scholar who dared to measure the universe. Through the Almagest and Geographia, Claudius Ptolemy's legacy became one of intellectual rigor, systematic thought, and the belief that knowledge could be codified, preserved, and transmitted across time and culture. He demonstrated that even in an era without modern tools, the universe and the Earth could be understood through careful observation, calculation, and reasoned inference. Every charted coastline, every mapped star, and every navigational route echoes the impact of his work. Ptolemy's vision of a measurable, ordered cosmos laid the foundation for centuries of exploration, discovery, and scientific advancement. In Alexandria, Ptolemy devoted himself not only to mapping the Earth, but to understanding the movements of the heavens above it. The precision of his observations reflected both an inherited mathematical tradition and his own meticulous discipline. Using instruments such as the astrolabe and the armillary sphere, he systematically recorded the positions of over 1,000 stars, each marked with an angular distance relative to the celestial equator and the ecliptic. These measurements formed the backbone of his star catalogue, allowing him to map the night sky with unprecedented accuracy. Ptolemy's methodology combined careful observation with geometric reasoning. He recognized that the apparent motions of planets could not be explained by simple circular orbits. To account for anomalies such as retrograde motion, he introduced the system of epicycles. Each planet traveled along a small circle, whose center moved along a larger circle around the Earth. This mathematical construct, though complex, allowed for accurate prediction of planetary positions. The ingenuity of this approach lay in its capacity to reconcile theory with observation, bridging empirical data and geometric principles. While his astronomical work established him as a leading authority on the cosmos, Ptolemy's contributions to geography were equally transformative. Building upon Marinus of Tyre and Eratosthenes, he compiled the Geographia, a comprehensive guide to the known world. The text included a detailed list of over 8,000 locations, each assigned precise coordinates of latitude and longitude. This coordinate system provided a standardized method for situating cities, rivers, mountains, and other geographical features, effectively creating a mathematical grid for the world. His maps, although limited by the knowledge of his era, introduced several innovations that would influence cartography for centuries. Ptolemy devised methods to project the curved surface of the Earth onto a flat plane, developing early forms of what would later become map projections. These methods allowed subsequent cartographers to preserve relative positions and distances with greater fidelity, establishing principles that remain foundational in modern mapmaking. The scope of Ptolemy's geographical knowledge was remarkable. His world encompassed Europe, North Africa, the Middle East, and parts of Asia, stretching from the Canary Islands in the west to the easternmost reaches of China. He divided the world into regions, providing not only coordinates but also descriptive notes on climate, terrain, and political boundaries. While some depictions, such as his portrayal of the Indian Ocean as a landlocked sea, were inaccurate due to limited exploration, the underlying system reflected an analytical approach that was revolutionary. Ptolemy also addressed the challenge of representing the three-dimensional Earth on a two-dimensional surface. He developed mathematical formulas for projecting longitude and latitude onto a plane, anticipating techniques that would be refined during the Renaissance. This systematic approach allowed for reproducible maps and established a framework that navigators and explorers could use as the world's geography expanded. In addition to geography and astronomy, Ptolemy made contributions to the study of optics. In his treatise Optics, he examined reflection, refraction, and the principles of visual perception. He conducted experiments to understand how light interacts with different media, including air, water, and glass. Ptolemy's work on vision also explored the angles and distances perceived by the human eye, laying early foundations for the scientific study of optics. Similarly, in harmonics, Ptolemy explored the mathematical basis of music. He analyzed scales, intervals, and tuning systems, connecting numerical ratios with auditory perception. This work extended the Pythagorean tradition, emphasizing the interconnectedness of number, sound, and cosmic order. For Ptolemy, harmony in music reflected the harmonious structure of the universe itself, a philosophical perspective that aligned with his broader scientific methodology. Alexandria's scholarly environment provided the backdrop for Ptolemy's achievements. The city's libraries and academic institutions offered access to centuries of accumulated knowledge. Scholars from various traditions, Greek, Egyptian, and Roman, exchanged ideas, ensuring a dynamic intellectual climate. Within this context, Ptolemy synthesized prior learning with his own observations, producing works that were both comprehensive and original. The preservation of Ptolemy's writings through translation and copying was critical to their enduring influence. During the Abbasid Caliphate, scholars in Baghdad translated the Almagest into Arabic, naming it Al-Majisti, or the Greatest. These translations preserved his mathematical tables, astronomical observations, and theoretical models. Islamic astronomers, including al-Battani, al-Sufi, and Ibn al-Haytham, built upon Ptolemy's work, refining his measurements and extending his methods. Similarly, the Geographia was translated into Arabic and later into Latin, facilitating its integration into European scholarship during the Middle Ages and Renaissance. In Europe, Ptolemy's influence surged with the rediscovery of classical texts, Latin translations of the Almagest and Geographia were studied by scholars and navigators, shaping the scientific worldview of the medieval period. Universities incorporated his works into curricula, teaching both the mathematics of the heavens and the principles of map-making. The Geographia, with its systematic coordinate system, provided the foundation for Renaissance cartography, enabling explorers to document newly discovered lands with increasing accuracy. Ptolemy's approach emphasized the interdependence of observation and reason. He sought to understand patterns and regularities, demonstrating that empirical evidence could be organized through mathematical analysis. This methodology influenced generations of scientists, laying the groundwork for the empirical and quantitative approaches that would characterize later scientific inquiry. Even as discoveries revealed errors in his specific conclusions, the intellectual framework he established remained essential. By the time of the Renaissance, Ptolemy's works were central to navigation and exploration. Cartographers such as Martin Waldseemüller and Gerardus Mercator used his coordinate system to construct maps that represented continents, coastlines, and oceans with greater fidelity. While European explorers like Columbus and Magellan encountered regions beyond Ptolemy's maps, his mathematical approach allowed them to integrate new discoveries into a coherent framework. Ptolemy's influence on exploration was thus indirect but profound. He provided the tools to measure, record, and communicate geographical knowledge systematically. Ptolemy's astronomical contributions similarly shaped subsequent scientific developments. Although the geocentric model he proposed was eventually supplanted by heliocentric theories, it provided a consistent framework for predicting celestial events. The rigor of his observations and the clarity of his mathematical models made it possible for later astronomers to challenge, refine, and ultimately replace his system. In doing so, they built upon the methodological foundations he had laid. Through his work, Ptolemy bridged cultures and centuries. His texts, preserved and transmitted across the Byzantine Empire, the Islamic world, and Renaissance Europe, connected generations of scholars. Islamic astronomers expanded and corrected his data. European navigators applied his geographical principles, and Renaissance thinkers used his methods to rediscover classical knowledge. The endurance of his work attests not only to its content, but to its systematic and reproducible methodology. By emphasizing measurement, mathematical reasoning, and empirical observation, Ptolemy demonstrated that knowledge could be codified, preserved, and transmitted across time. His legacy extended far beyond the confines of Alexandria. Globes, maps, celestial charts, and treatises all bear his influence. Even when his models were superseded, the principles he established continued to guide scientific inquiry. Ptolemy's life exemplifies the enduring power of human curiosity, the capacity to observe, reason, and structure the world in ways that transcend centuries. By the Renaissance, Claudius Ptolemy's works had traveled across cultures and centuries to become the cornerstone of European scientific thought. The Latin translations of his Almagest and Geographia introduced scholars to a system of knowledge that was both rigorous and practical. His geocentric universe, once unquestioned, now faced scrutiny as observations accumulated. Yet the structure he had built, meticulous measurement, mathematical prediction, and systematic documentation, endured as a guiding framework. Scholars recognized that even if the conclusions required revision, the method itself was a model of intellectual discipline. Cartographers and navigators in the 15th and 16th centuries relied heavily on Ptolemy's geographical principles. In regions like Italy, Germany, and Portugal, mapmakers studied his coordinate system to chart coastlines and new lands. The rediscovery of Ptolemy's work coincided with the age of exploration. European vessels ventured beyond the known world, documenting discoveries in the Americas, Africa, and Asia. Though Ptolemy's maps lacked these newly revealed lands, his projections and mathematical grids allowed explorers to place them coherently within a global framework. The influence of Ptolemy's Geographia is evident in the maps of Martin Waldseemüller, whose 1507 world map famously named America for the first time, and in Gerardus Mercator, whose 1569 projection revolutionized navigation, both built upon the coordinate principles established by Ptolemy, demonstrating the enduring utility of his approach. Even as inaccuracies became apparent, the underlying mathematical logic provided a template for improvement. The very act of mapping the unknown required a system capable of adaptation, and Ptolemy's work fulfilled that need. Astronomy, too, benefited from Ptolemy's legacy. While his geocentric model would eventually be supplanted by Copernican heliocentrism, it provided centuries of reliable planetary predictions. Scholars such as Tycho Brahe, Johannes Kepler, and Galileo drew upon his observations, refining them with new instruments and methods. Ptolemy had demonstrated the importance of precise measurement and mathematical modeling, lessons that became central to the scientific revolution. The Almagest, once considered dogma, evolved into a reference for empirical investigation. Ptolemy's contributions extended beyond geography and astronomy. His studies in optics laid groundwork for understanding the behavior of light and vision. Renaissance thinkers like Kepler revisited Ptolemy's experiments, using them to develop theories of refraction, lens function, and the science of vision. Similarly, Ptolemy's treatises on harmonics influenced the study of music, demonstrating the deep connections he perceived between mathematics, sound, and cosmic order. Across disciplines, his methodology, observation, measurement, and rational analysis became a guiding principle. The transmission of Ptolemy's work also exemplifies the interconnectedness of human knowledge. From Alexandria to Baghdad, through Islamic scholars, and finally into Renaissance Europe, his ideas bridged cultures and epochs. Islamic astronomers such as al-Battani and al-Sufi corrected, expanded, and preserved his findings, while European humanists translated and disseminated them further. The continuity of knowledge across time and geography underscores the universality of his intellectual contributions. By the 17th and 18th centuries, Ptolemy's legacy was understood more historically than prescriptively. Scientists appreciated the ingenuity of his methods, even as his specific models were replaced. The geocentric universe was abandoned, the enclosed Indian Ocean corrected, and planetary motion redefined. Yet the foundational approach, systematic measurement, quantitative reasoning, and synthesis of observation with theory, remained. Ptolemy's influence persisted in the principles of scientific inquiry, careful observation, methodical analysis, and the pursuit of knowledge through reasoned deduction. Modern geography and astronomy continue to reflect Ptolemy's influence. The coordinate systems used in maps, the mathematical approach to projection, and the cataloging of celestial objects all trace lineage to his works. While technology has transformed measurement, instruments, and exploration, the intellectual framework established by Ptolemy remains remarkably relevant. Global positioning systems, satellite mapping, and modern star charts are descendants of the principles he first articulated in Alexandria. Ptolemy's life exemplifies the enduring power of human curiosity. Living in a world without telescopes, computers, or modern navigation, he created systems that would survive empires, translations, and centuries of discovery. He demonstrated that the universe could be understood through a combination of observation, logic, and mathematics. His approach transcended individual findings. It provided a method for future generations to explore, measure, and comprehend the natural world. In reflecting upon Ptolemy's legacy, one sees not just the man or his maps, but the spirit of inquiry he embodied. The Almagest and Geographia remain monuments to the potential of human reason. They illustrate that with careful observation, disciplined measurement, and a commitment to intellectual rigor, the cosmos and the Earth could be brought into the domain of understanding. Even now, as we gaze at star charts or study global maps, Ptolemy's influence is palpable. His coordinate grids quietly underpin modern cartography. His star catalogue inspired centuries of astronomical study. The methodologies he employed, balancing theory with observation, measurement with reasoning, continue to guide scientific thought. Claudius Ptolemy, who lived almost 2 millennia ago in Alexandria, has left a legacy that resonates in classrooms, observatories, and research institutions around the world. In conclusion, Claudius Ptolemy was more than a scholar. He was a pioneer whose vision bridged ancient and modern worlds. His work unified mathematics, astronomy, geography, optics, and music into a coherent intellectual endeavor. By systematically observing and recording both Earth and sky, he created frameworks that allowed humans to navigate, explore, and understand the universe in ways previously unimaginable. From Alexandria to the Renaissance, from Islamic scholarship to modern science, Ptolemy's methods and insights continue to illuminate the path of knowledge, reminding us that curiosity, discipline, and reason are timeless instruments of discovery.